Electricity presents a unique problem for physicists. You cannot actually see electrons moving through a solid copper wire. Without a way to observe this flow, analyzing a circuit is like trying to measure the speed of a river while completely blindfolded. To quantify this current, 19th century scientists had to look sideways. They couldn't measure the electricity directly, so they relied on its guaranteed byproduct, the magnetic field it generates as it moves. Curious, this realization led to the Moving Coil Galvanometer. It is a device built specifically to take the invisible magnetic push of an electrical current and translate it into clear mechanical motion. When connected to a live circuit, a physical needle sweeps across a calibrated dial. The physical distance that needle travels tells you exactly how much current is flowing. The galvanometer acts as a mechanical translator. It takes the mathematical reality of the electrical universe and turns it into physical data we can read with our own eyes. The core of this device is a suspended copper wire wrapped tightly into a rectangular coil. This coil has a specific surface area, represented by the variable A, and a set number of individual wire turns, N. When electrical current passes through this wire, it generates its own magnetic field. Place permanent magnets on either side of the coil, and those competing fields push against each other, creating a twisting force known as torque. Flat magnets create straight field lines. As the rectangular coil rotates through them, the angle between the wire and the magnetic field constantly changes. This causes the twisting force to fluctuate, making consistent measurement impossible. The fix requires precision engineering. By curving the magnet faces into a bowl shape and placing a cylindrical soft iron core directly inside the rotating coil, the field lines are forced into a radial pattern. Now, no matter how the coil turns, the magnetic field is always perfectly parallel to its plane. This stabilization means the magnetic twisting force is always a constant, predictable number. The torque is simply the number of turns times the current times the area times the magnetic field strength. We have successfully converted current into physical rotation. But an object spinning endlessly is just an electric motor. To take a measurement, we have to make it stop. To arrest that spin, engineers attach a delicate spiral spring directly to the rotating axis of the coil. Every spring has a specific stiffness, known as a torsional constant. This is a physical value that dictates exactly how much restoring force the spring pushes back with for every degree it is twisted. As the electrical current pushes the coil forward, the spring winds tighter, pushing back harder. Eventually, they hit a dead tie. The mechanical torque of the spring perfectly balances the electrical torque of the coil. By rearranging this equilibrium equation to solve for the angle of deflection, we find that the mechanical movement is strictly proportional to the electrical current. This ratio, the amount the needle moves per unit of current, is called current sensitivity. Manufacturers can physically tune this sensitivity by adding more turns of wire, increasing the coil's area, or using a softer spring. By pitting the magnetic push of a circuit against the precise mechanical pull of a physical spring, the galvanometer provides an exact window into the electrical state of the system. There is a massive practical flaw here. The galvanometer is far too sensitive, peaking at just a few microamps. Connecting this instrument directly to the raw power of a standard household circuit would vaporize its delicate internal copper wires instantly. The ultra-fine copper wire has high resistance. Placed in series, it chokes the circuit, altering the current you're measuring. The solution is a bypass, a shunt resistance attached in parallel. Having incredibly low resistance, almost all the high amp current safely bypasses the delicate instrument entirely. Only a tiny fraction of the total current diverts through the meter itself. But because that fraction is mathematically locked to the total volume flowing through the main wire, the dial can be calibrated to read the massive current accurately. Every modern ammeter contains a highly sensitive galvanometer at its core, shielded from the full force of the circuit by this metallic bypass lane. Measuring voltage requires a different approach. A voltmeter measures the potential difference across a circuit, so it has to be connected in parallel. To avoid draining the very circuit it's testing, it must draw as close to zero current as possible. To accomplish this, we take the exact same core mechanism, but apply the inverse modification. We place an exceptionally large resistor in series with the galvanometer coil, severely restricting the amount of current that can enter the testing loop. Because of this heavy added resistance, artificially boosting the device's current sensitivity by adding more wire turns doesn't automatically improve its voltage sensitivity. More wire just adds more baseline resistance, canceling out the gain. Whether a technician is trying to read a trickle of current or a massive voltage drop, the solution is rooted in the same 19th century mechanism. We tame the invisible forces of electromagnetism by anchoring them against the physical, measurable limits of mechanical engineering.